Hi, in this video, we want to take a look at actually recording the time it takes to conduct computations in the bnlearn package. So what we want to do, want to get a feel for how much time savings do we get when we use parallel programming with the bnlearn modeling. All right, so something about parallel programming is that we always need to be mindful of the fact that in addition to the computation times, there's also like coordination and communication time for the computer to organize between the cores. Because of this, we can actually lose time. We can actually have the system take longer if we're not mindful of this. All right, so a situation where parallel computing will take a longer time is where let's say that each core is super high quality, super powerful. It's able to compute, a large amount of computations very quickly, very easily, and the entire project wouldn't take very long for one core to complete. Well, if I parallel program in that situation, what's going to happen is that each core will get done very quickly, but then the system is going to have to coordinate and communicate between the cores, and so then it will actually take longer for us to do parallel programming. We want to do parallel programming when the computations are too much for one core to accomplish. That's a rule of thumb. Now, we never really know truly which way is the best route until we start benchmarking. Benchmarking is where we run some computations and we look at the metrics afterwards to evaluate what is the best course of action. In general, benchmarking refers specifically to time, the recording of how long it takes for something to be accomplished. All right, so here, when I say benchmarking, I'm just talking about recording the time. And that's the most common usage of the word in computer science. So remember that the bnlearn package has some built-in parallel programming features that makes it super easy. All we have to do is establish the cluster, then tell bnlearn the name of the cluster, and boom, it takes care of everything for us. We don't have to do any more work. It's very nice, very easy. So when we do this, remember, we want to do this whenever the computations are enough that one core is going to get taxed from it, or it's going to take a long time for that one core to accomplish everything. And to record the time, we want to use system time. And what this does, this records two aspects of it's going to record user time, system time, then adds them up together to give us elapsed time. So there's three things that come out: user time, system time. Elapsed time is the sum of those two. What we're going to do, we're going to take the Hellfinder data set, which is in the bnlearn package, and we're going to use that to build some models. And we're going to clock how long it takes for each one of these. All right, so we can see that the Hellfinder dataset has 20,000 rows and 56 columns. So first thing we're going to do, we're going to benchmark the computations without parallel programming. So I'm just going to run it. I'm not going to have any clusters. I'm not going to do anything like that. I'm not doing any parallel programming. I'm just running it straight out of the box. And what we're going to do, we're going to do all of the constraint-based models. So the constraint-based models are the ones that take a cluster as an argument, and that is how bnlearn allows us to build the models very seamlessly with parallel programming. So what we're going to do, we're going to establish the network. We're going to make sure that there are no undirected arcs. Then we're going to use bnfit to fit the actual model. The first step of finding the network and the last step of fitting the actual model are going to be in parallel when we get to that point. On this step, we're not going to do any parallel programming at all. We're just running it as is. This is so we know, kind of like we have a baseline for how long it would take for each algorithm. So here we are going through and we are building the model. Then we're going to go through, we're going to take all of our undirected arcs, and what we're going to do for our undirected arcs, we're going to set arc, and I'm doing this twice. Now, why am I doing this twice? Well, remember that we can't have cycles in a directed acyclic graph. bnlearn wants us to use directed acyclic graphs. And so if the first time I try to set arc doesn't work, hopefully the second will work. And vice versa. So you notice I put down from equals 2 and 2 equals from. Down here I go from equals from, 2 equals 2. So I'm kind of making the assumption that this one is the better one. So if I can set arc either way, I want this one to be the one that sticks. Now, just to make sure I have the best possible result, I go ahead and I use choose direction to let the data speak. So if it's possible to go either direction on the arc, choose direction will go through and make sure that's the right way to go. If there's only one way I can go on the arrow without getting a cycle in there, then this isn't going to change anything. And honestly, it's just going to burn up some time. But time is what we're all about today. Now down here, I'm actually going to fit the model. So this is, I'm going to establish what are the actual parameters for the conditional probability estimates for our models. Okay, so you'll notice I put all of this into a function. Constraint without parallel. So for teaching, I hate using special functions. I really think it's a bad idea for teaching to use special functions. But in this case, I really didn't have a choice because I want to do network fitting, arc setting, and model fitting all under one time constraint. If I set these up as I try to do system.time and I have these not in the same function, it's going to measure the amount of time for each of those steps. And I don't want that. I want it all in one kit and caboodle. So I went ahead and put it into a function. And so right now, for without parallel, the parameter is just what algorithm to use. What constraint-based model do I want to use? And so what you'll see down here, I create a list to store all my models in. So I have my workspace is nice and clean. Everything's well organized. And each time I build the model, so on this step, constraint without parallel, fits the network, sets all the undirected arcs, then actually does the bn.fit and actually fits the model completely. So first step was find the network, then set the arcs, then fit the model. And all that is contained in this. System time is going to report what is the time for all of those steps together. And remember, system time gives me user time, system time, elapsed time, which is the sum of the two. Now, after I get done with this, what I'm going to do so I can store all of my data or all the output, I'm going to go ahead and make a data frame. It's a list of data frames. And what we're going to do, we're going to store, we are going to store the time that it took. We're going to store which model we are running, and did we use parallel programming, yes or no? So this was without parallel programming. Now let's go ahead and look at how it looks when we do benchmarking on the parallel programming. So everything's pretty much the same, but now there's something slightly different. When I find what the network is, I'm passing a cluster there, and the standard way of denoting a cluster is CL in R. And then everything else is just the same, except when I fit the model, I have a cluster here. Now, when I do when I take care of the undirected arcs, I'm not using a cluster at all because it won't accept one as an argument. But when we get down to fitting the model, after we have the network, after it's a directed graph, I use the clusters again. And so hopefully my goal is that by using the CL, by using parallel programming, I find the network faster and I fit the model faster. The part about converting undirected arcs to arcs, like I won't be able to use parallel programming to improve that unless I do a more in-depth technique, which I'm not going to bother with for a lecture. And then when I get everything, I'm going to store it in a list, and then I'm going to make a data frame from that list. So each time I'm going to go through each of the algorithms for fitting a network. We're going to establish the cluster that we're going to use, and you'll notice I'm using every single core I have on this machine. I'm building the model. So I'm establishing the network, setting arcs, and then fitting the model. And we are recording the time. Now you'll notice that on this process, I'm not actually storing what the models were, because for this lecture here, we care about computation time. We don't care about the models themselves. And then I stop cluster. All right, anytime I start using a cluster and I establish a cluster using make cluster, I also want to stop it. It's a good practice to always, if you open it, when you're done with it, you close it. And if you need a new one, just go ahead and make a new one. And you'll notice that each time I go through a different algorithm, I establish the cluster and then I stop the cluster. So establish the cluster, do the work, and then stop the cluster. And you'll notice the cluster is a parameter for that custom function that I made. And then we just go through and we tack on the model, and is it with or without parallel programming, just so that we, in a moment when we make the data frame, we're able to see what was going on. So now we're going to go ahead and, so M without is the results from going without parallel programming. So you'll notice that I'm using dplyr to take the entire list. So in the list, I've got the 3 times, I have the model type, and I have with or without parallel. All right, so then I've got 5 items, a vector of 5. What I'm doing, what this does, is takes that vector of 5 for each algorithm and then makes a data frame where each row corresponds to an algorithm. Once again, with what I'm saying is this is with parallel programming. I'm taking the 5 items for each of the algorithms and I'm making a data frame. And then I'm going through and making sure that the column names are the way I want them to be, making sure the column names are the way I want them to be. So we have, at this point, we have a data frame for without parallel programming. We have a data frame with parallel programming. And all the entries correspond to time, how long it takes to build the model. Now we just take with and without, we bind them together, and we have M. Now in the process, the class of the time got knocked off from where I wanted it, so I just put as numeric. And then I went ahead and reordered the columns, so it'll be a little bit easier to interpret. So we have the model, then we have, is it parallel, with or without, parallel programming, then user time, system time, elapsed time. And this is the order that system time gives it in by default. And so here, and I'll go ahead and order it by the model just so it's easier to compare the results. So like here, we can see that for fast IAMB, the total elapsed time without parallel was 10. And the total time with parallel was 3. And when you look at these numbers, realize that we have some rounding. They don't always add up correctly. Like we see 2 plus 3 equals 3. But elapsed time is usually the one you want to use. And we can go through each of the pairs of rows and we can compare. So here we can see that for grow shrink, it actually took longer to use parallel program than not. So that tells me that if I was going to do this later down the road, I would probably not want to do parallel programming if I'm going to use the grow shrink algorithm, because it looks like the communication and coordination between the nodes takes longer than what it's worth. All right, now what we do here is we go ahead and sort the, I'm going to take all the models and I'm going to sort them by the average time. So I have with and without for each model type, and I'm going to go ahead and take the elapsed time and just take the average. And I'm going to order them by the average time. And that's what this is. The tapply function is how I'm getting the average of with and without for each model. And then parallel, with and without, I go ahead and order it in the same manner, depending on, by how long it takes. We establish the colors we're going to use and name the colors. All right, now let's use ggplot to take a look at what the output is. Okay, so notice that I arranged it so that the faster models are on the left, slower models are on the right. With parallel takes less time, so it's on the left. Without parallel is longer, so it's on the right. And so this makes it easier to interpret what's going on. So I can see that overall, if I consider all of the models, that without parallel takes longer. Now, on my work machine, the machine I have at work, which is a beast of a machine, with parallel actually took longer. I was really surprised. I didn't expect that to be the case. But right now I'm using my wimpy UCF laptop, and on this machine, the cores are not as powerful. And so we can see that parallel programming actually improves the time, but not always. All right, so here we can see that there's an improvement, equal, improvement, improvement. Here, parallel programming actually slows it down. So I know that PC Stable, if I'm going to be using parallel programming, is going to have more communication and more coordination between nodes. Here we have an improvement. Here we have an improvement with parallel programming. Here, grow shrink gets worse. Okay, so for grow shrink, once again, we know that there's going to be some issues with the communication and the coordination between nodes. And HPC, we have an improvement. Now, we can do the same thing for the other two times that are recorded. So here we have user time. And here we can see user time is always less if I'm using parallel programming. So on this aspect, this is an improvement. But this is really, the elapsed time is what we actually care about, because that's the time that we are sitting there waiting on. Now for system time, we do the same thing. And when I plot it, we can see that parallel programming actually slowed it down almost every single time. When it comes to system time, we have equal. Things get worse with parallel programming, worse with parallel programming, worse, 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 worse. And it's better on grow shrink. All right, so this tells me, so I can split up these aspects of the time and I can get some feedback on, where is it that's slowing down. Truly overall, I care about the elapsed time. The elapsed time is the time that I'm waiting. If it's a long computation, I might have to run it overnight. I might have to run it for several days. Running it over lunch is super common, depending on the size of the project. So, the benchmarking can help set me up for identifying when should I do parallel programming, when shouldn't I. And so one thing you want to do, if it looks like you're going to have some long computations, take a smaller set of data, take a smaller computation load process and go through and run some test cases on benchmark, then decide, is it worth my time to do parallel programming? If it's not, just run it as is. If it is, go through the process of establishing it, which is also additional work on us. But you can, if you do this correctly, if you do this well, this can be a huge time savings. This can be the difference between a few hours and a few days of computations, honestly, if it's the right kind, if it's a big enough of a computational load. All right, that's all I've got for you. I hope you're enjoying the class. Take care and goodbye.